Alright, last thing we went over, I just briefly talked about the conservation of energy. But this isn't a physics class, so I'm not going to do that. Alright, we are about to go over, I guess you could say usually where this class stops, before we had to change the curriculum to finish the rest of the chapter. And that is Green's theorem. This is a physics topic, by the way. If you do take any more advanced physics classes, or even advanced numerical mathematics classes, you can use Green's theorem. You could use a lot of the stuff we've been covering in this section. So we're going to look at Green's theorem to evaluate a line integral and alternate forms of Green's theorem. Alright, so this theorem was named after a guy, he didn't live a long time, it doesn't look like, the English mathematician George Green. He looks like he died at the young age of 48. And this theorem states the value of a double integral over a simply connected plane region R. Remember, a simply connected means there was no gaps or anything. We remember the pictures that we drew last class period. Is determined by the value of the line integral around the boundary of R. Okay, so let me show you what we're talking about. So if you have a simply connected region R, and I'm going to write, I'll write the theorem down. That's simply connected. Alright, because it goes around the entire figure and it doesn't, there's no breaks in the line. So his theorem, the main thing that it says is that the value of a double integral over a simply connected plane region R is determined by the value of a line integral around the boundary of R. Alright, so that's simply connected. Let me show you something that's not simply connected, even though I've probably already put these same figures up the other day. So those are not simply connected. It's not that they're separated, even though they can't be. It's that, you know, this line doesn't go around every boundary. You have to go have a smooth curve here and here and here. So that's not simply connected. To be simply connected, it has to go around the entire figure. You have no breaks, so it's a continuous line. It's a piecewise smooth line or curve. Alright, so Green's theorem says, I've already told you what it means, but if we have R, some simply connected region, and it has a piecewise smooth curve C, so what am I talking about? Like the outside of this right here, this is a piecewise smooth curve. You know, maybe you can't describe it with just one path, but you could describe it with multiple paths. So, if you have a simply connected region with a piecewise smooth boundary, oriented counterclockwise, so you can see it's counterclockwise, right, because of the directions of the arrows. I can see those arrows there, so big going like that. If m and n have first partial derivatives in an open region containing R, then the line integral of m dx plus n dy is equal to the double integral over the region of the partial derivative of n with respect to x minus the partial derivative of m with respect to y dA. Again, let me tell you what that means. This theorem states that the value of a double integral over a simply connected plane region R is determined by the value of the line integral around the boundary of R. So notice the line doesn't cross itself around R, the R sub 1 up there. And it is piecewise smooth. You don't need it's not like R2 or R3 where you'd have to have, I guess you'd have to have many sets of different paths to be able to describe those. Also, you can see that it's oriented counterclockwise. All those are important. Alright, so I'm going to show you a few figures here. One figure is going to be, excuse me, vertically simply, and one's going to be horizontally. I said simply, I meant simple. It's going to be vertically simple, the other's going to be horizontally simple. To me, just seeing the pictures, it makes it have a little more meaning. Maybe not a lot more meaning, but a little more meaning. All right, so you can see it is oriented counterclockwise. It has here, there's a C sub 1 and a C sub 2. And the curve C is simply the entire thing. And that is considered to be vertically simple. All right, horizontally simple, instead of having y equals x, we have x equals y. All right, so we consider that to be horizontally simple. All right, so let's see how we can use Green's theorem to evaluate a line integral. So write down this line integral. Maybe not. I clicked something in the ebook and it went crazy, sorry. So you can see we have an M here and an N here. This is 15.4. And it's all about Green's theorem. So C is the path from 0, 0 to 1, 1 for y equals x cubed and from 1, 1 to 0, 0 along the graph of y equals x. So if you think back, I believe we've actually we've either worked this exact same problem using line integrals or something that was maybe it was y equals x squared and y equals x cubed. But let me show you the picture and maybe this will jar something loose from your brain. Maybe you'll have a little bit of total recall. I can go back up to that, but I want to show you the picture. Remember that? I mean, I could have swore we did the exact same one. It's just that the m and the n are changed here, so. But C is the path from 0, 0 to 1, 1 for y equals x cubed, and 1, 1 to 0, 0 for y equals x. So is that closed? Yes, that's closed. Is it oriented counterclockwise? Yeah. And, you know, we had said that things are simply connected. It's simple if it doesn't cross itself. So when we were talking about vertically simple and horizontally simple, that was because it doesn't cross itself. It doesn't, you know, we don't have part of the line crossing over this line. Okay, so it's simple and it's connected. And of course it's a region. All right. So what is the partial derivative of m with respect to y, and what is the partial derivative of n with respect to x? We need those. So you see your m and your n. The partial derivative of m with respect to y is 3y squared. The partial derivative of n with respect to x is 3x squared plus 3y squared. All right. So if we want to apply Green's theorem to this, I'm going to copy this equation back down. You might just want to write yours by the equation. I just need a little more space. So maybe I can put it right here. All right. Remember what that's equal to according to Green's theorem. Up here. This is Green's theorem. It's equal to the double integral over the region of the partial derivative of n with respect to x minus the partial derivative of m with respect to y dA. Okay, so we know what the partial derivative of m with respect to y and n with respect to x is. So that means we can rewrite this This is going to be the double integral over the region, and I'm just writing down the definition. Partial derivative of m with respect to x minus the partial derivative of m with respect to y dA. Alright, so that's going to be the double integral over the region, and we'll figure out the boundaries in a second. And then the partial derivative of n with respect to x is 3x squared plus 3y squared. And then minus the partial derivative of m with respect to y was 3y squared. dy dx. So do you see what's going to cancel out? Alright, so those are going to cancel out. Now we need to figure out our boundaries. Alright, kind of like when we were doing the centroid problems, and almost everybody missed the boundary on the centroid problem. Alright, the x is on top and the x cubed is on bottom. So my boundary for my y here is from x cubed to x. I mean, I can't really say top minus bottom. I mean, like we would do if we were doing area, but it's like the same kind of concept. The top curve is x and the bottom curve is x cubed, and we're bounding the y because of the dy. All right. Now, the outermost boundary we want to be constants. So can you tell me the constants or how the x is bounded? Yeah, look, 0's right here, 1's right here. If for some reason, maybe you don't have the graph or you can't see the graph, you can always set the two equations equal, like that. And then if I move the x over, I'd have x cubed minus x equals 0. And then I could factor out an x. And that would be x squared minus 1 equals 0. And then if I set each one of these equal to 0, I get x equals 0 and x equals plus or minus 1. Now we don't have the minus 1 because these graphs aren't extended this way, and we don't have the graph going back down like that. Alright, so we don't have the minus 1, we just have the 0 and the 1. Alright, so that's 0 to 1. So it turns out to be a pretty easy double integral. Yes, there is such things as an easy double integral. It's just 3x squared dy dx. So integrate that, you get x cubed, right? Wrong. You have to integrate with respect to y. Alright, so it's going to be 3x squared y evaluated from x cubed to x. Got to make sure we look at the order of integration. Alright, so remember you plug these in for the variable that you integrated with respect to. So this is going to be, if I plug it in for the y, it's going to be 3x cubed, because you'd say x times x squared minus 3x to the 5th. Okay, so that's gotten rid of the y's. Now all we have to do is integrate with respect to x. Okay, so this is what? 3/4 x to the 4th minus 3/6. Do you mind if I put 1/2? You will allow it. X to the 6th. 0 to 1. So if I plug in a 1, I get 3/4 minus 1/2. If I plug in a 0, I get out a 0. So that's 3/4 minus 2/4. That's 1/4. Now, Green's theorem doesn't work with every line interval. Why is that? Because of all those restrictions, right? It has to be connected. It has to be simple, meaning the lines will not go over themselves. It has to be counterclockwise. Okay, so you do have some restrictions there. And so, you know, we just do it the old-fashioned way, the other way that we were doing line integrals. All right. So now, let's think about using Green's integral. You know, it's going to be the outside of the region. But let's think about or see how we would use Green's integral to calculate work. I said Green's integral, Green's theorem. It is an integral, but. All right. Let's say that we had this force. Y cubed I plus x cubed plus 3y x squared j. Looks kind of familiar. All right. And let's say while subject to the force F, a particle travels once around the circle of radius 3. And I'm going to give you the circle of radius 3. Now, the circle of radius 3 that we're looking at is x squared plus y squared equals 9. But I'll show you a picture. Even though you should be able to picture that circle in your mind. All right, there we go. Kind of looks like a circle. Now it looks more like a circle. So you have a particle that's traveling around that circle. We're going to use Green's theorem to figure out the work done on that circle. So we already know by Green's theorem, and you already have this written down, but you may want to write it down again, that the line integral of y cubed dx plus x cubed plus 3xy squared dy was equal to the double integral over the region of 3x squared dA. You know, we figured out how to set all that up. We changed it to dy dx, and we changed our boundaries, and we had to take partial derivatives. We plugged them in, and we got all, that's what we got. Okay. So since we're in a circular motion, since we have a circular motion, what's the coordinate system that relies or brings more meaning to circular motion? The polar coordinate system, right? So in the polar coordinate system, x equals r cosine theta, right? I'm not going to say what y equals because we don't need it. Because we just have an x squared right here. What is dA equal to? No, we don't have any y's and x's anymore. R dr d theta. All right. So what we're going to do is we're going to say our work is now equal to the double integral over the region, which we'll put in our stuff there. We'll put in our boundaries. We know we're going to have, instead of dy dx, our dA is r dr d theta. And we found out from Green's theorem that once we did the partial derivative of n with respect to x and m with respect to y, and we set it up in the formula, we got 3x squared. So that's going to be 3 times x is equal to r cosine theta. So 3 times r cosine theta squared. All right, so what's my radius? That's my dr. Well, we were told a radius of 3. 0 to 3. Now, how far does this simply connected path, smooth curve C, how far does it go around? The entire circle, right? So that's 0 to 2 pi. All right, so I have the double integral, 0 to 2 pi, 0 to 3. I have a 3. I can write that 3 in front if I want to and not worry about it until the end. Now I am going to have, when I square this inside, I have an r squared and a cosine squared. So that's going to be r squared times r. That's going to be r cubed cosine squared. So first, we integrate with respect to r. So I have 3 times the integral from 0 to 2 pi. So when I integrate with respect to r, that's r to the 4th over 4. Cosine squared theta. And we have to evaluate that from 0 to 3. So when I plug in a 3 for r, what's 3 to the 4th? 81? Yes. So when I plug in a 3, I'm going to have 81 over 4. When I plug in a 0, I'm going to have 0. Does everybody see that? So I'm going to have 3 times the integral from 0 to 2 pi of 81 over 4 times cosine squared theta d theta. All right. Let's go ahead and take the 81 over 4 out so we don't worry about it. So I've got to say 81 times 3. 243 over 4. Now for the integral that most of you have forgotten. Hopefully not. I mean, I want to think that I've taught you at least 1 or 2 things. But remember, that's 1/2 times 1 plus cosine 2 theta. You can't just integrate cosine squared. It's not sine squared, sorry. So we're going to bring the 1/2 out, yeah. We don't have to worry about that. So that's going to be 243 over 8 times the integral of 1 plus 2, I'm sorry, 1 plus cosine 2 theta. Can't believe that we're actually doing this. It's so awesome. So what's the integral of 1? Infinity? Is that what you said? Theta? That's our variable. Whoa, you wouldn't know that because I didn't write d theta. All right, and then what's the integral of cosine 2 theta? 1/2 sine 2 theta. All right, and now we're going to evaluate that from 0 to 2 pi. All right. So we have 243 over 8 times. So I'm going to plug in 2 pi. 2 pi plus 1/2 sine of 4 pi minus 0 plus 1/2 sine 0. All right, sine of 0, we all know, is 0. Right? Well, if you travel around twice more, you're in the same position as 0. So that's 0. So we have 243 over 8 times 2 pi, which is 243 pi over 4. All right, so that's how you can calculate work if you know the path that a particle is traveling. If a particle is traveling in a circular motion around a radius of 3, this is the force exerted on the particle. So that's the field. And using Green's theorem, that's how we can calculate work. The reason we changed it over to polar again is because we were in a circular motion. And it's easier to do integrals in a circular motion using polar coordinates. We don't want to use x squared plus y squared equals 9 and do all that. Because then we have lots of square roots, and it becomes a lot more complicated to work it out in a rectangular coordinate system.